Buckle your seatbelts, because we're about to take a 10,000-foot view about what this entire course, Abstract Algebra II, is going to be about, looking at the 8 different course objectives that are listed on your syllabus. So let's get started right away with objective number 1. The first objective of this course is that you're able to differentiate among and provide examples of algebraic objects and their associated morphisms. Now that sentence is a mouthful. What does it really mean? What it really means is that you're able to give me examples and to tell the difference between various algebraic objects, and algebraic objects are things like sets, for example, and morphisms, which are functions between those objects that have certain properties attached to them. So, for instance, between the objects that we call sets are morphisms that we call functions from one set to another set. And that's kind of our basic object, our basic algebraic object and basic algebraic morphism. And of course, last semester in Abstract Algebra 1, you learned about groups as a kind of object, and the morphisms that connect one group to another were the homomorphisms. They were homomorphisms because they had additional structure. They weren't just functions, they also respected the structure that made a group something more than a set, namely the product that makes a group. Also in linear algebra, you learn about vector spaces. Those are the kinds of objects you study in linear algebra. And the morphisms that connect one vector space to another vector space are called linear transformations. Again, these are functions from one vector space to another that turn an element of a vector space, a vector, into an element of another vector space. But they also have properties that respect the structure, the additional structure on that vector space, namely a linear transformation has the linear property, that the function applied to a sum gives you the sum applied to the functions, and then likewise with scalar multiples. Well, of course, in Abstract Algebra 2, we're going to meet different kinds of objects. And specifically, the kinds of objects we're going to be most concerned with this semester are rings and fields. And each of those kinds of objects is going to have its own kind of morphism as well. The rings will have ring homomorphisms, and the fields will have field homomorphisms. And so we're going to want to know what are the differences between these things, what are some examples of this particular kind of object and particular kind of morphism. So the first outcome is that you're able to give me some examples of rings and fields, and what is the difference between these things? So what's the connection between rings and fields and sets and groups and vector spaces, and what are the important differences? Outcome number 2 is to take another look at finite groups. This is where we go back to Abstract Algebra 1 and we sort of take it a couple of steps further. In particular, we'd like to answer the question, how do you break down a finite group into smaller pieces? We're going to do that in 2 different ways. The first is to construct a subgroup lattice. So for an example, take the finite group D3, the dihedral group of the triangle. This is the different symmetries that take a triangle into itself, an equilateral triangle into itself. To make a subgroup lattice is to say, well, the smallest possible subgroup inside of D3 is just the trivial subgroup, but in between the trivial subgroup and D3 itself are other subgroups in the middle. Namely, there's one subgroup of order 3, there's one subgroup of order 2, both of them are cyclic, and so we can kind of visualize the subgroup structure of D3 by writing down a little lattice like this, ordered by inclusion. The second way to do it, and this way is going to be even more useful going into the latter part of our course, is to look at the composition series of a group, which is just a different way of writing down a subgroup lattice, but paying attention not just to the subgroups, but specifically to the normal subgroups. Inside of D3 there is a unique normal subgroup that's not the trivial subgroup, and that is a Z3, which is a normal subgroup of D3, and likewise, the subgroup of Z3 is going to be the trivial group itself. So here we have kind of a series of normal subgroup inclusions here that makes a composition series. And what makes it a composition series is that when we take the quotient of each of these normal subgroups, we get something that's abelian. If we take the quotient of D3 by Z3, we end up with something isomorphic to Z mod 2. And when we take the quotient of Z mod 3 by the identity normal subgroup, we obviously get something that's isomorphic to Z mod 3. So we'll be looking at composition series as one of the really important ways of breaking down a finite group. And the big result in that circle of ideas is the Jordan-Hilder theorem, which is going to tell us that pretty much the composition series attached to a group are unique in some sense or another. It's going to be a very important theorem for us going forward. Outcome number 3 is to look at actions of finite groups. What does this mean? If we talk about describing and comparing the actions of a finite group on a set or the action of a finite group on a vector space, what an action tells us is that groups can somehow behave like functions on other sets. What do I mean by that? Well, think about the symmetric group for a second. Say the symmetric group on 3 symbols. We can think of that symmetric group as acting on any 3 symbols that we like. So for instance, the set containing the objects A, B, and C has an action of S3 on it. What does that look like? Well, it looks like a correspondence by which we can associate to an element of S3 some permutation or some function from the set ABC to itself. So we might associate to the transposition of 1 and 2 in the group S3 that transposition that takes A and B and just trades them back and forth with one another. So that's just an example. We can define this in a lot of different ways. We can also look at the actions of groups on vector spaces. So for instance, D3, that dihedral group of the triangle, we can think of as acting on the xy plane, R2. How? Well, let's just take an example of an element of D3, T, the transposition, and just imagine that being associated to the linear transformation on R2, which takes xy and replaces it by minus xy. Well, this is how we usually envision the dihedral group acting. Namely, this is just taking this triangle and flipping it about the y-axis. So groups can, in that sense, behave like functions on other sets, or on vector spaces, and so we're going to look into that a bit. Outcome number 4 is our next big milestone in the content of our course, and that's rings. So we want to be able to define a ring, including rings of polynomials and matrices, and then to describe ideals within them. Ideals are like the sub-objects inside of rings that we care the most about. Again, what is a ring? A ring is an abelian group with an extra operation. So the classic example is just the ring of integers. Well, integers is a group, an abelian group, under the standard addition operation, but if we add an extra operation, that of multiplication, we actually get some additional structure. Inside of this ring we can add and we can multiply. We can also subtract, again, because z comma plus is a group, every one of its elements has an inverse. But the one thing we can't do inside of this ring is we can't divide. If I divide two integers one by another, we're not guaranteed to get an integer as the answer. So we can add, we can subtract, we can multiply, but we can't necessarily divide. And that's what prevents this ring of integers from being something more than a ring. We can also look at examples like rings of polynomials. Let's consider the set of all polynomials that have integer coefficients. That's going to form a ring, again under the same operations of addition and multiplication of polynomials. But again, we can't divide, because when I divide a polynomial by a polynomial, I don't always get a polynomial. We can also look at rings of matrices. So the set of all n by n square matrices with addition and with matrix multiplication as the operations. That again forms a ring. But again, we don't necessarily get division because not every n by n square matrix is invertible under multiplication. And again, ideals. Ideals are just the sub-objects inside of rings that we happen to care the most about. So, for example, inside of the ring of integers, we can consider the set of all even integers as being an ideal, a sub-object inside of that ring. We'll talk more about what that means, obviously, in due time. Outcome number 5 puts the icing on the cake and takes rings and extends them to fields. So we want to be able to define fields using and in contrast to rings, and provide examples that are both finite and infinite. So first of all, what is a field? A field we're going to think of as just a ring with everything on it. Every possible property that we could hope to be true inside of a ring to make all the arithmetic that we take for granted every day work the way that it works will be present inside of a field. So classic example are the rationals. So the rational numbers with addition certainly are an abelian group. If we endow that with multiplication, we get a ring. But we get something better than a ring, because not only can we add, subtract, and multiply just like we could in the integers, we can also now divide any rational number by another rational number, and the answer is going to be a rational number. There's of course one exception to that rule, and that is that we can't divide by 0. But everything else we can divide by and get a rational number. So the rationals are a prototypical example of what it means to be a field. Now that's an example with infinitely many elements in it. Well, what about z mod 2? Where we have 0 and 1, and we use addition modulo 2 as the operation that makes that an abelian group. Well, if we also endow that with multiplication modulo 2, it turns out that we also get a field. But this field, unlike the rational numbers, has finitely many elements in it, just 2 elements. So are there other examples of fields that are finite? Well, sure. And the finite fields are going to play really important examples of fields as we go forward this semester. Outcome number 6 now has to do with how algebra works in the more abstract context of working inside of a field. So we know, for instance, how to factor some polynomials over the rational numbers, over the integers, over the real numbers. But how does this work in a more general setting? We'd like to be able to determine how to factor polynomials over various fields, and then also to answer the question about unfactorability, to use and prove irreducibility criteria. So again, when we're saying factoring, usually we think of factoring as being an art form, but what we'll see this semester is that there's some things about factoring that can make it more systematic. As an example, over the rational numbers, we take a polynomial like t squared minus 4. That polynomial factors the difference of two squares, t plus 2 and t minus 2. But if we change that a little bit, make it t squared minus 5, suddenly this doesn't factor over the rational numbers anymore. It does factor, though, just over a different field, a slightly bigger field, the field of reals. T squared minus 5 factors into t plus radical 5 times t minus radical 5. But if we change that a little bit, make it t squared plus 5, now this doesn't factor over the reals anymore. But it factors over the complex numbers, because we can factor t squared plus 5 into t plus I radical 5 and t minus I radical 5. So the question of factorability really has a lot to do with factorization over what field. Once we get to the complex numbers, though, does anything not factor over C? Big question, one of the central questions that we'll answer, hopefully this semester. Outcome number 7 is the really capstone of our course. Determine the splitting field and the Galois group of a polynomial and connect it with the roots of that polynomial. Now this sounds like a mouthful, and it really is. The basic overview is that to a polynomial we're going to associate a group called its Galois group. So for instance, to the polynomial t squared minus 5 we might associate the group z mod 2. And the purpose of that group is going to be manifold, but one of them is that that group is going to act on the polynomial's set of roots. This is again a group action in the way we talked about in outcome number 3. So what does that look like for t squared minus 5? Well, t squared minus 5 has two roots, radical 5 and minus radical 5. And the Galois group action on that group, on that set of roots rather, is going to be twofold. The identity element of z mod 2 is just going to be the identity on each of those roots. And the non-identity element of z mod 2 is going to be the transposition of those elements one to another. So the question here is, what does this Galois group of a polynomial tell us about the polynomial itself? And can we figure out the Galois group of a polynomial without knowing the roots of the polynomial? And the really big question, what does the Galois group tell us about how to solve a polynomial equation? It's going to be one of the motivating questions of this semester. Finally is outcome number 8, which is to help you develop into better writers of mathematical proof. So we want to look at how to discover, sequence, and effectively communicate mathematical proof, both in writing and out loud, one to another mostly. So this is going to come in 3 different main areas, and each time I score one of your proofs, I'm going to score it in each of these 3 different dimensions. We would like for your proofs to be logical, precise, and also to be well-written or well-spoken if you're doing it out loud. So just to expand a little bit about what each of these means. A logical proof uses, first of all, valid inference. Uses a sufficient amount of detail, but not too much detail, right? We would like for you to write just as much as you need to exactly make the point that you're making, but no more, and that each of your inferences is valid, that you're using quantifiers appropriately, and that A implies B really means A implies B. Precision in proofs really has a lot to do with terminology. So are you using the language of our subject accurately and appropriately? And are you also using notation to convey the meaning of each of your proofs and each of your arguments carefully and precisely, so that a reader is not left to wonder what in the world is going on? That feeds into the last topic, which is what makes a proof well written. Well, of course, spelling and grammar are big topics. Is your proof persuasive? Have you actually convinced the reader that this proof should actually be true? And does your proof flow? In other words, if you go on a tangent talking about some object A, but you haven't told us what A is yet, then that's not a proof that flows very well. So make sure that everything before you begin to discuss it is well defined and well motivated. So these are the dimensions on which I'm going to be scoring your proofs. And don't worry, I'll go pretty easy on you early in the semester, but this is one of those skills that we really want to work on as the semester goes forward. So those are the 8 objectives that we'll have for Abstract Algebra 2 this semester. Again, this was a really quick overview. Feel free to look back at this video again throughout the semester to make sure that what you're learning as you go along is connected with these main objectives of the course.